Let's continue our treatment of the rotational partition function by now considering what is the case for nonlinear molecules. Now, we can write down a general classical expression for the energies of these by using three different rotational constants in the x, y, and z directions. And I'll write this sort of general formula like this, where the three components of J here are three components of an angular momentum vector J. So if we have an angular momentum vector J, it has components Jx, Jy, Jz, and we can write down a general energy in terms of this in three rotational constants. Now you notice the number 3 comes up a lot. That's because rotational degrees of freedom are 3 for a nonlinear molecule. There are only 2 for a linear molecule. So we're going to need to take that into account. Now, because of this, we generally cannot write down a nice formula for the energy levels, the quantum energy levels for a rotor that has 3 distinct rotational constants as drawn here. But we can at least quote for you the results for the rotational partition function. Now, one of the things I need to specify is that these 3 rotational constants generally are listed in descending order. That is, A is the largest, then B, then C. No special reason for this, but it allows us to order those a little bit. And you can see that this is the convention that's followed in the table below, where I've shown some of the rotational constants for a couple of common molecules, water, SO2, and acetone. Now, when one goes through a fair amount of math, one can show that the rotational partition function for this nonlinear molecule looks something like this. We've got the square root of pi, again over a symmetry number, and I'll talk about that in just a minute. And then we'll have a square root of Kb times temperature cubed divided by the product of the 3 rotational constants. So it's actually not a very complicated formula, but I'll just say that getting there is not something that we need to do in this class. We can further write this if we adopt the same notion of rotational temperatures that we had in the last film. We could take each of these rotational constants, divide it by the Boltzmann constant, and get 3 rotational temperatures that I'm drawing here. And then we can express the rotational partition function in terms of those rotational temperatures. And it would look something like this. We'll end up having square root of pi over sigma, and we'll end up with T cubed divided by the product of the 3 rotational temperatures. Now, it's quite easy to verify that with this, we now have a rotational partition function that doesn't have units. We've got units of temperature cubed in the numerator here and units of temperature cubed in the denominator here. We can also see that as the rotational constants are larger, we're going to have a smaller partition function, just as we did for the linear case. And when these rotational constants are smaller, it should result in a larger rotational partition function. All right, so what can we say about the general behavior of this? Well, first of all, we can see from these rotational constants listed in the table below that water is the lightest of these 3 and it has the largest rotational constants. So once again, we see that light mass also results in large rotational constants. It will result in also large rotational temperatures. And this combination of factors means that the z that we get from this, the partition function, is typically going to have fewer states available. It's going to be smaller. When we have heavier molecules or molecules that are more spread out, that's what causes these rotational constants to be very small. So here SO2 is much heavier than water, even though it's a comparable size, it's a triatomic, but you can see already we've lost an order of magnitude and more off of each of these rotational constants. All right, so when we go to acetone, acetone isn't especially heavy, but it's all spread out. It's got a much larger area, and the moment of inertia depends upon how far away the masses are from the center of mass. So once again, we see a reduction by about an order of magnitude, well, at least in the first rotational constant, relative to SO2. So once again, we can see that if a molecule is spread out, it's going to have small rotational constants, and this is going to result in more rotational states available. So this gives you a good rule of thumb when you look at a molecule. If the molecule is heavy or if it's big, one can determine that in fact it has fairly small rotational constants. Now I want to finish by talking a little bit about the average rotational energy, and for that I'm going to have to re-quote for you the result for Z rotational for a linear molecule. It's 1 over sigma times the rotational constant times beta. And for this nonlinear molecule, it's going to be this more complicated function that looks like 1 over sigma times the square root. And I'm going to combine some things together here, but we're going to end up with beta cubed times ABC. Now I've written these in terms of beta so that when we calculate the average rotational energy, and actually I should make this a small e, it's minus d beta of the log of Z rotational. It'll be easier to do that. These other things don't depend upon B rotational, so log of Z rotational will be negative log of sigma b minus log of beta, and the derivative of log of beta is just going to be 1 over beta. So in fact the average energy of rotation is just 1 over beta, which is simply kT. If I do the same thing here for the nonlinear molecules, I've got a bunch of stuff here that will separate out as part of the logarithm that doesn't depend on beta. So I'm going to have logarithm of, I'll just say some stuff, minus the logarithm of beta raised to the 3rd power to the half power, so beta to the 3 halves. And so when I take the derivative of this partition function with respect to beta, I'm going to end up with an expression that looks like 3 over 2 beta, or 3 halves kBt. And so we see that what makes a difference in going from linear to nonlinear is we have a slightly larger rotational energy because we have an additional degree of freedom. And we're beginning to see here a correlation between the number of degrees of freedom, which was 2 in the case of linear molecules and 3 in the case of nonlinear molecules. There's a correlation between those and the amount of average energy that they have. We'll talk a little bit more about that when we discuss the equipartition principle.